Welcome to lesson 57512, where we are looking at using a second derivative test to determine relative extrema. And you're like, well, didn't we already do this? Yeah, we did. We used the first derivative test for relative extrema, where we found the critical points. And then we analyzed the sign chart, and we knew that if we had changes from the first derivative negative positive, we got a local min. If we had changes from a positive first derivative to a negative first derivative, we had a local max. The first derivative test was very straightforward and quick, easy to use. However, it doesn't always work. To use the first derivative test, we needed two things to be true. We needed to be able to find the critical values of f of x, and we needed to be able to determine the sign changes on f prime of x. So what do we do if we cannot find or cannot use the first derivative test? There is another test to help us figure out if we have a relative min or max. So consider f of x where we're not given an equation for f of x. However, we do know that f prime of 2 is equal to 0. What does that tell us about it? Well, it tells us that we have a critical point, right? And what does this not tell us about f of x? Well, I don't know how it behaves around f prime of 2, right? At x equals 2, f of x has a relative min if I have, whoopsie, not drawing, if I have this sort of shape to it, correct? If I have a negative derivative coming into it. Now, I need to probably identify that this is f of x, and I have information that f prime of x is a critical point. What the first derivative test has allowed us to figure out is if I had negative first derivative coming into a positive first derivative, at that case then I had a relative min. Here, if I have a downward shape, then I knew I had a relative max. And same idea here, we're really looking at, f of x, knowing that f prime of 2 was 0, that could be fine. The other case that could happen for us when we have f prime equal to 0 is we can get that, coming in slightly horizontal tangent line there for a moment and then back up into increasing function. So once again, I'm looking at f of x and I know that f prime of 2 was 0. In this case, we have neither a min nor a max. So those are really the three scenarios that can happen if I have a critical point at f prime of 2 or f prime of any c value. What can I figure out about this? In this example, what if we also knew that f double prime of 2 was negative 5. So what if I knew that? What if this piece of information was readily available to me? What does that tell me? Well, which example would that be a case of? If f double prime of 2 is negative, that means I'm concave down, right? Oh, that would be this scenario, case 2. And that would tell me then that f has a horizontal line at f prime of 2. I should put a 2 in there. See if I can write over top of that, f prime of 2. And we know that it's concave down at f of 2 because I was given information that the second derivative was less than 0. That is our case number 2. This idea behind the that's the idea behind the second derivative test. If I can figure out the second derivative on my critical point, I can determine whether I have a relative max or possibly a relative min, right? If I have concave up for second derivative at that critical point, then I've got a relative max. The second derivative test, just to reiterate and summarize here, we know that if the second derivative is positive, If the second derivative is positive on that critical point, then we have a local min. If the second derivative is negative, we have a relative max. Let me see if I can get my finger to be this. Smartboard, cooperate, please. Okay, so second derivative, if it's negative, and we know that C is a location of a critical point, we will have a maximum. If the second derivative is equal to 0 or undefined, then we have to, we cannot really determine whether there's a min or a max. We need more information. It could be a local min, it could be a local max, or it could be neither. We'd have to go see if we could figure out a first derivative test and do the sign chart. I like the second derivative test because sometimes it's actually faster and easier than doing a sign chart. So, important to note, the second derivative test is not a test for points of inflection. It's really set up for determining relative extrema, and thus the name second derivative test. Points of inflection, we use the second derivative, but however, it's not referred to as a second derivative test. That's just kind of semantics. So you get a little summary there of first derivative and second derivative test. When should we use the second derivative test? In most cases, use and apply the first derivative test. Do your sign charts just like you would normally. However, there are two cases that appear on the AP exam that would require the second derivative test, and that would be when working with the table of values, and we'll go through an example like that, and then when working with just like an implicit curve where we have to have x and y's. That's tough to make a sign chart of just x values when you've got x and y's involved. So example 1, told you we would work with a table of values. So example 1, oh wow, we got all kinds of information. We know f of x, we know f prime of x, and they're giving us f double prime. So identify all the x values where there is a relative min. Justify using the second derivative. Okay, so identify all the x values where there's a relative min. First off, and I don't quite know what, oh, I do know what's behind my box here. First off, I need to have critical points, right? Look for critical points. Remember how a critical point is defined? F prime of x is equal to 0 or undefined. I find that right here. Here is f prime, and I get 0 there and a 0 there. So both 2 and 7 are x values where we have critical points. Now it says identify where there's a relative min. I can use my second derivative. I can't use information around that critical point because it's not close enough. Look at the gap here. It goes from 2 to x equaling 5. Who knows what's happening in between that interval? So there's not enough, close enough information to really determine whether I have, a positive first derivative to a negative first derivative. Positive to negative would have implied a relative max. But that's not going to be solid enough evidence. So let's roll to the second derivative test and look at, oh, I've got a positive second derivative. That means I'm concave up there. And I have a negative second derivative, so that means I'm concave down when x is 7. Where would I have a relative min? Right here, wouldn't I? So I love the pictures for second derivative. Concave up gives me a relative min. My wording would be a relative min of 7. Ooh, let's put at, of 7, yep, we do have that information, occurs at x equals 2 because f prime of 2 was equal to 0 and f double prime was equal to 4, so f of x is concave up. The other thing you could identify, you could say which is greater than 0, if you wanted to tag that on there. Now let's identify where there's a relative max, and we could see if we have first derivative 0, that's critical point, second derivative negative, that means concave down. Oh, well then at 7, we must be hitting a relative max. And that relative max value is the y value of the original function. So I get a statement that says a relative max of -2 occurs at x equals 7 because f prime of 7 equals 0 and f double prime of 7 equals not 4. How about a -3 on that? I need to correct that. So f of x is concave down. I would even add on, so f double prime is 7 of 7 is -3, which is less than 0. Thus, we get concave down. Letter C says, identify all x values where there is a point of inflection. Point of inflection in our brain, you should be connecting that with double prime. I need f double prime of x equaling 0 or undefined. And we need sign change, don't we? The sign changes of f double prime. Do you see that happening? Well, now I'm going to focus in on my second derivative. Here's a 0. Here's a 0. And then I can identify sign changes on each side of it. A point of inflection occurs at 5 because f double prime changes sign at x equals 5. What is the equation of the tangent line to the curve of f of x at x equals 5? This is just a nice review. See if you can hit pause and write this out for me. So at x equals 5, I look on my table and I see that f of 5 is a 3. So that gives me an ordered pair of 5, 3, doesn't it? And then I also need to know what the slope is at 5. So f prime of 5 is -1. And now I can write that equation. Y minus 3 equals -1 times, oops, not a y, x minus 5. Good old review. Okay, on to the next fun piece. So example 2, the function f is twice differentiable. That just means we have a derivative existing for all real values of x on the first derivative and the second derivative. It also tells me I've got nice smooth curves, right? I don't have any pokey places for along the way on f or f prime. So it's a nice twice differentiable function, also means it's continuous, and has exactly 2 critical values. Selected values of f prime, the derivative, are shown in the table. Okay, I see that. Along with the graph f double prime. At which values of f does f of x have critical points? Okay, critical points. F prime equals 0 or undefined. I guess I'm going to go to the chart and look for where I see a 0 and a 0 when I'm looking f prime. That occurs at x equals -3 and x equals 3. For each critical point, determine if it has a local extrema at the given x value, or state that it can't be determined. Now I'm going to roll into, so I know that f prime of -3 was 0. I'm just going to make 2 columns here. And f prime of 3 was also equal to 0. Critical points. Now let's see if we can figure out what the second derivative is at -3. Second derivative at -3, oh, it's somewhere up there. Let's say it's 5 1/4. Kind of rolls off of our page bit, doesn't it? Second derivative at 3, what do we get for information there? At 3, ooh, it's 0. Okay, let's analyze this one first. On the left, at -3, x is, well, this tells me I'm concave up since this is greater than 0. Second derivative greater than 0 and a critical point is going to be a relative minimum at x equals -3 because f prime of -3 equals 0 and f double prime of -3 is equal to 5, which is greater than 0. Thus, we're concave up. The next one, it's definitely a critical point, right? But then I look at second derivative information, and this makes it a potential point of inflection. So it would be neither a min or a max. X equals 3 Could we determine, is there a sign change? Yeah, because I can look at f double prime and say it was negative to positive. This actually, x equals 3 is a POI since f double prime of 3 changes signs. We'll go ahead and indicate that it went from negative to positive just to add extra information in your notes. Negative to positive at x equals 3. You know what? I think rather than stating at 3, we need to say f double prime of x changes sign from negative to positive at the location x equals 3. So the left and the right side, we can see that. Okay, example 3. Let g and h be twice differentiable functions with g prime equaling h of x times x minus 2. The graph of h lies below the x-axis for all real values of x. They just told me that h is negative always, right? Because it lies below the x-axis. Does the graph of g have a relative min, max, or neither at x equal 2? And give your reason. Well, let's first verify that it's a critical point. So is x equals 2 a critical point? If it's not, game over. So we need to get to look at g prime of 2 to see if h of 2 times, 2 minus 2, I'm subbing x in. I don't even really care what h of 2 is because I'm going to get times 0. Anything times 0 is 0. So definitely we have a critical point. Now, let's go roll into what g double prime is. So this is, yes, a critical point at x equals 2. Second derivative. I think I'll do x first because I've got to do a little bit of derivative work there, don't I? So I'm into product rule. That's going to be an h prime of x times x minus 2 plus derivative of x plus minus 2 is a 1 times h of x. Now let's examine this at 2. Second derivative at 2. Oh, there we get that 2 minus 2, which is really a 0. And h of 2. That means g double prime of 2 simplifies down to just h of 2. And you can write a 0 in there if you wish. Now, I know that h of 2 is less than 0 always because they gave me h lies below the x-axis. So, I have a critical point and concave down at x equals 2. So concave down, draw it. That's going to lead us to the conclusion that at x equals 2, x equals 2 is a relative max. Because it is a critical, let's write it out, because g prime of 2 equals 0, and the other thing that helped us was g double prime of 2 was less than 0. Perfect. I don't have to say at x equals 2 because it is implied in my notation for that function notation. All right, loving this, right? Let's go to example 4. Ooh, this time we get a table, but these are probably my least favorite, where they have like positive, negative, just sketchy information. Hopefully it's enough for us to come up with stuff. The function f of x is continuous for all real values. The table above includes information about f prime, f double prime, and selected values in intervals of x. So for each x equals -5 and x equals -2, determine whether it's a local min or local max or neither. Explain your reasoning. So first off, there has to be a critical point, right? Verify critical point. So I want to look at, what are we at? F. F prime of -5, does it equal 0? It does indeed. There's 0. And what about, maybe I'll work over here, critical point, when we have f prime of -2. Oh, also a critical point. So yes. Now, let's look at f double prime. We can roll forward, right? F double prime of -5 is -2, which is less than 0. So we're concave down. This is a relative max at x equals -5. Conclusion, right? Second derivative test. At x equals -2, we got to look at the second derivative. Second derivative gives us 0. That's not helpful, is it? Not helpful. Okay, but when I look at this table, it's written just a little bit differently. It gives us intervals around the point. So I could really do a sign chart at -2. Oops, not that second derivative. I could do a sign chart for first derivative. So let's do sign chart. Yeah, I'm running out of room. Up here. So f prime at -2 says I have negative, ignore that, to positive. Negative to positive. That means I'm going down, back up for f. Relative min. Conclusion, relative min at x equals -2. And this was by first derivative test. And this other one was by, I used second derivative test. However, I probably could have used, oh, I couldn't, could I? Because I didn't have enough information by second derivative. I just went immediately to second derivative test because it's fast and easy. I just needed to know what first derivative and second derivative were. All right, part B, classify any additional known values of x where there is a relative extrema. All right, there is one more spot where we have a first derivative that's negative. So f prime of 13 is 0, which implies it's a critical point. So it has the potential to be a relative min or max. And if we look at, if we try to do sign chart, oh, I don't have an interval around it, do I? So I can't do sign chart. But I can use second derivative test. Using second derivative test, I can see f double prime of 13, that's a double, now it looks like a triple, double prime at 13 is a 1, which is greater than 0, so that means we're concave up. Ooh, it's a relative min. X equals 13 is a relative min. Second derivative test. Part C, at which values of x must the graph have a point of inflection? Hopefully you're connecting point of inflection by connecting that to f double prime equals 0 or undefined. Do we have any situations on our chart where that's the case? I'm just going to clean off my chart because it's getting messy. Second derivative negative, right here, undefined, and right there. Looks like we've got some potential ones right in that vicinity, don't we? So we have points of inflection at -2 because my signs change, and my signs change at x equals 3, and do my signs change at 11? It does. This makes me a little nervous just because that interval, you know, jumps away at 13, so that's sort of hard. I'm going to say x equals -2 and x equals 3 are POIs f double prime of x equals 0 or undefined, and f double prime changes sign at each x equals 2 and x equals 3. That's a negative 2. Perfect. Part D. The line tangent to the graph of f of x at x equals 6 is used to approximate f of 10. Will this approximation be an over or an under estimate of f of 10? And explain your reasoning. So we know all about, I'm just going to clear my screen. We know all about tangent lines, right? We could build a tangent line at x equals 6. Do we have enough information on our chart? At 6, I don't have specifics, but I do see that 6 does lie right in here. And I do know the second derivative is negative when we are in that interval. So I know that f double prime of 6 is less than 0. Which means we're in, which implies concave down. And if I'm concave down, it'd be something like that. And let's just throw here's 6, here's 10. So here I have, location of 6, and here I have a location of 10. Now, draw in your tangent line at 6. This is your tangent at x equals 6. And since I'm concave down, oh, look at the overestimation going on. If I had used my tangent line to estimate f of 10, there definitely would be some inaccuracy as well as just being overestimate. So this is on the interval f double prime is less than 0, meaning f of x is concave down. Therefore, the tangent line at x equals 6 will overestimate f of 10. Makes sense? Draw the picture. That always helps. Second derivative can tell us whether we're over or underestimating a linear approximation, which is what this essentially is. All right, we're at 27 minutes and going into example 5. So I'm going to cut this video off. This would be a good break point for day 1, and we're going to roll into day 2.